Okay, so we will continue on here. And so far we've covered confidence intervals for one sample numeric variable. Okay, and so now we're going to do a hypothesis test for one sample. Again, numeric variable. Everything in Chapter 9 is on numeric variables. Okay, so hypothesis tests always have hypotheses, right? So you have a null hypothesis, and for when you're dealing with a numeric variable, it's going to be mu is equal to some number. I'm just going to put a box here. And then the alternative is going to be mu does not equal that whatever that box is, or greater than the box, or less than. Okay? So the null hypothesis always has equal sign. And then the alternative not equal or greater than or less than based on the question. This should look familiar because you guys did hypothesis testing for one sample but with a categorical variable in last week's homework. And what was the difference there? Instead of mu, you used p, okay? But it was p is equal to some proportion, or p is greater than that, or less than that, or not, you know, something like that, okay? This week, numeric variable, you've got mu. Okay? So when you look at your data, your sample of data will have n, your sample of data will have x bar, and your sample of data will have s. Okay? And you will come up with your test statistic. T is equal to x bar minus mu 0, which is basically the box. Okay, mu 0 is the value. Whatever number shows up in your hypotheses, that's mu 0, divided by the standard error. Okay? So mu 0 is the value that appears in your hypotheses. And in your notes, what is the standard error when you've got one sample dealing with a numeric variable? You guys wrote this earlier in your notes. Your standard error when you have one sample, s over the square root of n. Okay. So this, when you put everything together, you get a value, your t, okay? So this is your test statistic. What do you do with the test statistic? The next thing, so once you have your test statistic, you look it up in the table. You look it up in the reference table. Yeah, in the t table, because we're dealing with the t distribution, t statistic, okay? Reference table to get your p-value. To get your tail area and p-value. This should sound familiar. Okay? It should sound very similar to what you did last week when you were dealing with proportions. When you did hypothesis test for proportions, it was very similar in process. It's just the elements were different, right? We didn't have x bar, we had p hat, and we didn't have mu 0, we had the p in the hypothesis, and we didn't have standard error here. I mean, we did have a standard error, but it looked a little different, okay? It's very similar, but a little different. Everyone has a face. The individual elements are a little different. Okay, so then once you have your p-value, what are your conclusions, right? So if the p-value is greater than alpha, what do you decide? So if the p-value is greater than alpha, yeah, do not reject the null, okay? Not guilty verdict. And if the p-value is less than alpha, reject the null, okay? So although it sounds like you might be tempted to say you accept the null, but we never say we accept the null, okay? Just like a jury never says we find the defendant innocent, they always say not guilty, because we're always presuming innocence, okay? So either you reject or you don't reject. Okay? All right, so that's the steps for a hypothesis test for one sample. Is that okay? All right, I'm going to put a problem up on the board, possibly similar to a problem you might see next week. And we'll try this out, okay? All right. Someone claims that their vending machine earns an average of $160 per week. Okay? Just selling cans of soda or whatever, okay? But maybe, you want to see if this is true, okay? So you gather data on 10 randomly selected weeks. Okay? So from those 10 weeks, the machine earned an average of $154 with a standard deviation of $11. Okay? So is this evidence that the machine earns less than $160 per week on average? Okay. So I'm going to walk you through this problem, okay? So we're going to identify the hypotheses. And our hypotheses here is that mu, because we're looking at the mean, is 160. We want to know, is it equal to 160? And then the alternative is that they're asking, is this evidence that the machine earns less than 160? So our alternative here is less than 160. Okay? our observed mean is what? X bar is equal to 154. Okay. What is the standard error?
$11.
That's the standard deviation. So the standard error is s over the square root of n. So it's going to be 11 divided by the square root of 10. Eleven divided by the square root of 10, 3.479. Okay, our test statistic is going to be t is equal to x bar minus mu 0 over the standard error. So our t, what is our x bar? 154. What is mu 0?
160.
160. It's the value that shows up in our hypotheses. Standard error?
3.479.
3.479. This is going to be our t. So our t is 154 minus 160 divided by the answer I have. I get negative 1.725. That's my t. Okay? How many degrees of freedom do I have? How do we find degrees of freedom? N minus 1. Okay. So degrees of freedom is n minus 1. So how many degrees of freedom do I have?
9.
I have 9. N is 10, so degrees of freedom is 9. So my test statistic is 1.725, and my degrees of freedom is 9. So what is the corresponding tail area, which in our case is going to be our p-value? What is the tail area? What do I have to do for this?
Go to the 9.
Yeah, I go to the table, and I'm looking up negative 1.725, or because it's symmetric, I can look up 1.725 in 9 degrees of freedom. So what do I have?
It's going to be between 1.833 and 2.2.
Yeah, so it's going to be in between here and here. So I got 1.725 in 9 degrees of freedom. And so that means my tail area is between 5% and 10%. Can everyone see that?
Yes.
Okay. So my tail area, here, let me use red, is between 10% but more than 5%. Okay? And do you remember the rules about one-sided and two-sided tests from last week? If you have a less than or greater than sign in your alternative, it's a one-sided test, so your tail area is your p-value. So I have my p-value is between 5% and 10%. Okay. So if my alpha is 5%, what is the decision we make regarding the null hypothesis? So is my p-value bigger or smaller than alpha? Yeah, my p-value is greater than alpha. Okay? Okay? My p-value is greater than alpha, so we reject or do not reject? We do not reject. My p-value is greater than alpha, so we do not reject the null hypothesis. And so, our final conclusion to answer this question, is this evidence? Is this being the fact that when we picked 10 random weeks, it earned an average of $154? Is this evidence that the machine earns less than $160 per week? No. Okay, we would say we do not have evidence that the machine earns less than $160 per week. Okay. Now, does it prove that the machine earns $160 a week? No, it doesn't prove that, but it's just saying you picked 10 random weeks and the average was 154. That's not enough to say it makes less than $160 per week. We had a question earlier?
Yes, just a quick question. How did you figure out that the alpha was 0.05 again?
I'm just giving it to you right now. If alpha is not stated in the problem, assume alpha is 0.05. Yes?
So the tail was greater than? What does that do to our p-value?
What the tail is greater than what?
You said it was from last week when you were explaining E. You said it.
Okay. So here, if you have a less than or greater than sign, it's a one-sided test. If you have a not equal sign, it's a two-sided test. And when you have a two-sided test, you double your tail area to get your p-value. Does that sound familiar? It should sound familiar, okay? Maybe you forgot these things, but it should sound familiar. If you have a not equal sign in the alternative, whatever your tail is, you double it to get your p-value, okay? When you had proportions, you could look that up in your z-table and you get an exact p-value. When you're dealing with means, you have to look it up in the t-table and you don't get exact values, you get a range. If it was not equal, then you double it. Okay. Yes?
How do you identify when you're supposed to take the non-equal into your alternative?
So, yeah, when we read this question, it says, is there evidence that the machine earns less than 160 per week? So there we put in the less, okay? If it says, is this evidence that the machine earns something other than 160, okay? Something other than 160 means maybe it's more than 160 or maybe it's less than 160, okay? Then in that case, we would put a not equal sign in the alternative. Is that okay? You might see something like this next week, or you will. You will. I'll just say it, okay? All right. So far today, we've covered confidence intervals for one sample and a hypothesis test for one sample. We just did the hypothesis test for one sample. Again, everything we're doing today is numeric variables. So I'm going to cover confidence intervals for 2 samples and hypothesis tests for 2 samples. Okay, and that will be it for the material, new material I'm covering, and then if we have time left over, I'll throw in maybe a few problems for you guys to try out. Okay, again, all of these things are different, but they're also similar. Okay, the elements and individually themselves are different, but the overall concept is the same. And I don't want us to forget that, okay? Because if you just see everything all separately, then it becomes overwhelming. It feels like there's too much to learn. Okay, if you say this is get an overall idea of the framework, and you can just say the elements differ from here to here to here, then it's easier. Okay, so we will do a confidence interval. For 2 samples. Again, numeric variable. We have a question. No, you have half an hour, okay? That's it, all right? Yeah, but I'm only giving you like 2 or 3 problems, okay?
35 minutes. Come on. 35.
Okay, I've always given you guys about 33 minutes, okay? I've never enforced the hard 30-minute thing on the quiz, okay? Yes?
So is the clue for the hypothesis question, is this evidence?
That's going to tell you about whether you should use a greater than or less than sign or not equal sign in your alternative hypotheses. The statement in the question, it will say, is this evidence of this? Or do a test to see if this, okay? Those statements will tell you how you should set up your hypotheses. Remember, the null hypothesis always has an equal sign. So you're always looking for what you should put in your null hypothesis. And then the alternative, you got to decide, do I use a greater than, a less than, or a not equal? And that depends on the reading of the question. Yes?
But compare the confidence interval.
But a confidence interval it should say do a confidence interval somewhere in there. We'll talk about this. Okay. We have another question.
Like we normally test if it's a hypothesis question with like this, like what's your hypothesis?
Yeah, somewhere in the test it will probably say do a test to do this. Okay. And somewhere in there it'll probably say what is the test statistic. Okay. And that means you're dealing with a hypothesis test, okay? Confidence interval for 2 samples, okay? So always, the big picture behind a confidence interval is we don't know what the population looks like. We see sample, or samples, in our case with 2 samples, and based on what we see in the samples, we want to make a conclusion about the population. We've always said that, okay? Confidence interval for 2 statements. We want to make a statement about mu1 minus mu2. Okay? So an example is we compare the heights, the average heights of men and women. So if we compare the average heights of men and women, we want to know what is mu1 minus mu2. Basically, we're asking what is the mean difference between the average height of a man and the average height of a woman. And so what seems like a likely value for mu1 minus mu2? 5 or 6 inches, right? We're basically saying the average man's height is about 5 inches, 6 inches taller than the average woman's height. Does that make sense? Okay, that's basically what we're trying to say here. Okay, so our resulting interval might be 5 to 6 inches. Okay, we are saying that the average man's height is between 5 to 6 inches taller than the average woman's height. Okay? That's all. And so that's the premise that we're going for. Notice this doesn't say what the average height of a man is. It doesn't say the average height of a man is around 5'10", 5'9", or whatever. And it doesn't say that the average height of a woman is around 5'4", 5 whatever. Okay? It doesn't say that. It just says we're just talking about the difference in average heights. Difference between the average heights. Okay? Equally, I could, instead of saying that the average man's height is between 5 to 6 inches taller than the average woman's height, I could flip this around if I decided to use women first in the sentence. I could say that the average woman's height is between what? 5 and 6 inches shorter than the average man's height. Right? So an equivalent statement the average woman's height okay? So I could say this, and these two things are saying the exact same thing. Right? Okay, and so when we make our confidence intervals, we're just going to say, I'm X blank % confident, so a generic statement, generic confidence interval statement is going to be, I am blank % confident that the average, or the mean, maybe I'll say mean value of blank, this is population 1, is between blank and blank higher or lower, depending on your values, than the mean of population 2. Okay? So essentially I'm just generalizing this thing that we said about average height differences between men and women to a generic statement of population 1 and population 2. And just talking about the mean value of whatever we're looking at instead of heights or whatever. Okay? Okay? So, this is a confidence interval for the value of mu1 minus mu2, or mean of population 1 minus the mean of population 2, is going to be equal to x bar 1 minus x bar 2. This goes in the center of our interval, plus or minus t star times the standard error. Okay? And do you guys remember what the standard error was that I had you guys write down in your notes early on? Yeah, S1 squared over N1 plus S2 squared over N2. So plugging that in, we get x bar 1 minus x bar 2 plus or minus t star times the standard error which is this. How are you guys doing? Hold on. All right, I appreciate you guys copying notes, not playing on your phones, but you know, I know it feels like a lot. And it is a lot, but it's also doable. It's also doable, okay? You don't... just imagine being a car mechanic, okay? Do you have to know every single thing about every single different car?
It helps.
I mean, it can help, but basically, you know, if you're dealing with a regular combustion engine car, you're going to see the same type of things. You're going to see, you know, they all have an engine and they all have, you know, oil filters and spark plugs and fuel pumps and this and that. And if you understand the overall concepts, you'll be fine. Individual cars, they're going to have different things and there's going to be different little nuances for here and that. But if you can see the overall picture and say, oh, well, this is what role this plays, then it's okay, all right? So all of these things, the confidence intervals, they all have, you know, something, okay? Basically, an estimate of this thing goes here. This is what we call the point estimate, plus or minus a number you look up in a table, or this is some number that you just find multiplied by the standard error, and then the conclusions you say, well, if something is in between here, then we go with that. Okay, so let's try out a problem here, okay? We'll say, what is the average, or what is the difference? So let's go back to our problem. What is the difference in difference in heights of the average male and average female? Okay, so we go out. Let's say we surveyed 12 men and 10 women. Okay. The average height of the 12 men surveyed is, we'll say 70 inches and has a standard deviation of 3 inches. And we'll say the average height of the surveyed women is 64.5 inches with a standard deviation of 3.2 inches. Okay? And I'm going to say make a 95% confidence interval for mu1 minus mu2. Okay. So let's go through and label our data. We have two samples. We have sample 1, and do you want to call sample 1 the men or the women? Okay, so sample 1 will be men, and we have sample 2, and that will be the women. So we have N1, X bar 1, and S1. We have N2, X bar 2, and S2. What is N1? 12. Okay, we have 12 men. What is N2? 10 women. X bar 1. 70, the mean height of the men in our sample. X bar 2, 64.5. S1, 3. S2, 3.2. Again, whenever you do a problem, it's going to make your life so much easier if you list out the pieces of data that you have, okay? Don't try to jump straight to your answer, because you might mess that up. List off which one's n and which one's x bar and which one's s, and your life will be a lot better, at least for that problem, okay? All right. From this, let's figure out our t star, okay? So t star we get from the table. Okay. So t star depends on our confidence level. What is the confidence level that we're using? 95% confidence. And what is our degrees of freedom? Okay, so degrees of, we're only going to have one thing for the degrees of freedom. So degrees of freedom is always going to be n minus 1, but which n do I use? Do I use the 12 or do I use the 10? We use the 10. We always use the smaller n. Okay? Use the smaller n. So degrees of freedom is going to be 10 minus 1, 9 degrees of freedom. So if I go to my table, 9 degrees of freedom, 95% confidence, what do I use? 2.262. T star is 2.262. All right, so let's plug all of this into our confidence interval. The equation for the confidence interval, x bar 1 minus x bar 2 plus or minus t star times the square root s1 squared over n1 plus s2 squared over n2. Okay, so let's go. 70 minus 64.5 plus or minus t star 2.262 times the square root 3 squared over 12 plus 3.2 squared over 10. Okay? Just want to make sure everyone with me so far. All I've done is taken this thing which we had before and I've just plugged in the numbers. Okay, so what's 70 minus 64.5? 5.5, right? So this part over here becomes 5.5. And I have plus or minus 2.262 times this thing over here. So I'm going to do 3 squared over 12 plus 3.2 squared divided by 10. Okay, and I get 1.774, and I want the square root of that. So I get 1.3319, or 1.332. And I multiply that by 2.262. So I have 5.5 plus or minus basically 3.01. Okay. So I have a huge margin of error here because I only looked at 10 and 12 women total. So my confidence interval is going to be 5.5 plus 3.01. So I have 8.51 on the high end. And on the low end, I have 5.5 minus 3.01. So 2.49. So basically 2.5 inches to 8.5 inches. Okay, this is my confidence interval. And I would say the important conclusion is is I write, I am 95% confident that the average height of men is between 2.49 and 8.51 inches taller than the average height of women. And that is the final statement we make there. Good? Kind of? Let me just do a very, very, very quick recap. All right. Did everyone copy this down? Okay. So just a quick review of the different confidence intervals we've seen. Okay? Okay. We have seen confidence intervals for 3 scenarios. One sample, categorical variable. Let me just see how I can fit all of this. We've got one sample, and it's a categorical variable. We have one for one sample, and it's a numeric variable. And we have 2 samples, numeric variable. Okay? So the one sample categorical variable is a confidence interval for P. One sample numeric variable is a confidence interval for mu, and 2 sample numeric variable is confidence interval for mu1 minus mu2. Okay. Here our data has an x and an n. Or maybe I'll say n and an x, which is the n is sample size and the x is a count. Over here our data, n, x bar, and s. And over here our data is n1, n2, x bar 1, x bar 2, s1, s2. Okay. And here you need to calculate p hat, which is equal to x over n. Your count over how many you have total. It's your sample proportion. Okay. All of these, your center or the point estimate here it's going to be p hat. Over here it's x bar. And over here it's x bar 1 minus x bar 2. Okay? It's basically whatever this thing is. So whatever this thing is, it's how you estimate it using your sample. P becomes p hat. Mu of the population becomes the sample mean. And mu1 minus mu2 becomes x bar 1 minus x bar 2. Okay. Your standard error. The standard SE these p hat minus times 1 minus p hat over n. Here, oops, getting ahead of myself, s over the square root of n, and here you have a standard error. It's that, okay? Okay. So you put everything together and you have p hat plus or minus z star times the standard error. Over here you have x bar plus or minus t star times the standard error. And over here you have x bar 1 minus x bar 2 plus or minus t star times the standard error. Okay. So all the confidence intervals, they have the same different parts, it's just each one looks a tiny bit different. Okay, you have, so the generic form is a point estimate, goes in the center, plus or minus a critical value times the standard error. Okay. So you learned this in chapter 7, and then we covered this and this today in chapter 9. The stuff for the proportions, that was from chapter 7. And then this is chapter 9, and this is also chapter 9. Okay? It's not that awful.
It's pretty awful.
There are much worse things in life.
Yeah, no, geometry is horrible, but it's so hard.
I love geometry.
Yes, but you love stat much more than geometry.
That's also true. You guys don't love statistics? So all the confidence intervals, this last row, they're all in the form of a point estimate plus or minus a critical value times the standard error. Okay? Here, point estimate, x bar 1 minus x bar 2, okay, times the critical value t star times the standard error. Over here, the point estimate is x bar. Okay, the point estimate, remember, here we're making a confidence interval for p. Over here, we're making a confidence interval for mu. And lastly, we're making a confidence interval for mu1 minus mu2. Okay? You don't know p. P is in the population. Your best guess for p, based on your sample, is p hat. That's what we call a point estimate. You don't know mu. Your best estimate for mu is x bar. We don't know mu1 minus mu2. Our best guess for that is x bar 1 minus x bar 2. That's all I'm saying. What's that? I can only assume you're concealing your excitement for the next thing we're learning here. Yeah, all right. Not concealing his excitement here. Okay. So we have one more thing to cover.
You're joking, seriously, you're joking.
I'm not. What is can we just, you guys are pretending like your life is so hard, all right? I'm just trying to present all the material in a way that makes sense here. Yes? Yeah, we can do that. Sure. Let's see. Okay. Yeah, if we got time. Okay. Last thing that we're covering today. Okay. Hypothesis testing. For how many samples? For 2 samples. And what kind of variable are we dealing with? Numeric. Everything today is on numeric variables. Okay? So again, hypothesis testing, we always have a pair of hypotheses, a null hypothesis and an alternative hypothesis. Null hypothesis always has what in it? Equal sign. Good. At least some of you guys are paying attention. So mu1 is equal to mu2. This will always be your null hypothesis, okay? Or we can equivalently write it. Okay, last week we did P1 is equal to P2, or we said P1 minus P2 is equal to 0. Here, because we're dealing with mu's, we can also say mu1 minus mu2 is equal to 0. And then the alternative is either going to have greater than, not equal to, or less than, right? And the alternative equivalently. There are 2 ways to write the exact same thing. We can say not equal to, greater than, or less than 0. Okay. So one nice thing, the hypotheses will always have 0. Okay. So for 2 samples, the hypotheses always have a 0. We'll always have a 0 if you use this form, okay? Or it's just mu1 is equal to mu2, mu1 doesn't equal mu2, or greater than, less than, okay? This should look familiar, because last week we did pretty much the exact same thing, except instead of mu's, you had p. Are our brains still working? We can kind of remember this? Okay. Some of you guys are giving me a thumbs up. My favorite students here, okay? I don't have favorites. Huh? I saw thumbs up. I saw thumbs ups, man. It's a secret, okay? I can see it from my vantage point. You guys can't see it, all right? You guys should be giving me thumbs up, all right? All of you. My self-esteem isn't so low that I would do that, all right? Okay. Data. All right. When we have 2 samples and it's numeric variable, we've got sample 1 and we have sample 2. What are the 3 pieces that come from sample 1? You guys, we've done this so many times. We have n, we have x bar, and s, okay? But because they come from sample 1, we put a little 1 next to them. And for sample 2, we've got n2, x bar, and s, okay? Again, we put little 2's to indicate that they're coming from sample 2. I feel like I'm just repeating myself every time, okay? But it's all right? Now we're going to have to figure out our standard error. We've seen this several times today already. And what does that look like? S1 squared over N1 plus S2 squared over N2. And what is our degrees of freedom? N minus 1, but we use the smaller n. Our test statistic, T, is going to be x bar 1 minus x bar 2 divided by the standard error. When you have a test statistic, what's the next thing you do? You look up your test statistic in the table, okay? And then look it up in the table. Okay, which table are we using? T-table, good. And then we get a p-value, right? We get a tail area which we use for our p-value to get our p-value. Okay, basically if it's a one-sided test, the tail area is the p-value. And for a two-sided test, we do 2 times the tail area to get our p-value. Okay, and how do we know when we have a two-sided test? Not equal sign and the alternative hypothesis. See, you guys are making me so proud. All right? Yay! All right. And then you take your p-value and then you compare that to alpha, and if it's smaller, you reject the null, and if it's bigger than alpha, you don't reject the null, right? It's all the same. It's all the same. It's just the. Is that okay? It's not so awful. It's not so awful. I don't like your negativity here, all right? How would you feel if you were like?
No, it's not you.
I know.
The greatest math teacher I've ever had. This material is this hard.
I haven't heard that before. All right.
Not you, it's us.
It's, all right, so let's. Yeah, absolutely. Oh, where did it go? Shoot. Okay. Hang on. All is.
Control Z.
Yeah. I know. Here we go. There we go. You take your p-value and you compare it to alpha to make your conclusion, right? So maybe I'll write that down, okay? And the rules are the same as before. So compare your p-value to alpha to make your conclusion. If your p-value is less than alpha, you reject the null, and if your p-value is greater than alpha, do not reject the null. Okay. I feel like I've said that so many times and written it down that I don't feel like writing it here again, but if you want me to, no. Okay. Is that okay? So we'll do a quick recap of hypothesis testing. Yes?
So T is test statistic and T star is the...
So T star, the stars only show up when you're doing a confidence interval. Z star and T star, those only appear for a confidence interval, and those you look up in your table. Or the Z star, I gave you 4 numbers that you had to memorize or have written down, and then the T star, you just look at your confidence, and then you look at your table. So quick review of hypothesis testing. Okay, so all hypotheses, or all hypothesis tests, start off with hypotheses. Okay, then you gather info from your data. Okay, specifically, they'll have a standard error. Okay. Then you calculate a test statistic. You look up the test statistic. To get a p-value. And lastly, use the p-value and alpha to make a decision and conclusion. Okay, so all hypothesis testing, it's got this setup, okay? And we've covered 4 hypotheses tests. Let's see how I can do this. I might run out of space. Okay, we have hypothesis tests for one sample of data, and it's a categorical variable. We have a hypothesis test for 2 samples of data, categorical variable. Okay, we have a hypothesis test for 1 sample, numeric variable, and we have for 2 samples also numeric variable. Okay, so let's talk about the hypotheses for each of these.
Professor,
Yes,
where can we find the videos of the lectures?
they're on the website.
Yeah, well, what part of the website? I looked last week and I couldn't find it.
On the lecture video.
There's a link page that says lecture videos. All right, we will continue. All right, our null hypothesis for, we got p is equal to some value here, okay? Instead of a box, I'm just going to put in some number 0.30, okay? But again, just know that this, of course, this value here depends on the problem, okay? Your alternative hypothesis is p does not equal that, or is greater than that, or is less than that. I love you guys, all right? It's the best class ever. All right. And I got P1 for 2 samples. I've got 2 P's, all right? So P1 minus P2 is equal to 0, and the alternative, again, something other than that. Maybe I'll just do greater than 0, okay? Or again, less than 0 or not equal to. Again, depending on the problem. When we have a numeric variable, what do we have? Instead of p, we're using mu. And so mu here is equal to some number, 42, who knows? Not necessarily 42, depends on the problem. And then we have mu something other than 42. Okay, and lastly, what do we have when we have 2 samples and we've got a numeric variable? Mu1 and mu2. So we'll say mu1 minus mu2 is equal to 0 versus mu1 minus mu2, something else, maybe less than 0. Okay?
Good question.
Yes?
On those last 2,
Mm-hmm.
is it the same as not equal to, less than, and greater than?
Yeah, all of these, okay?
Okay, got it.
All of these we can do, can be, you know, less than, greater than, or, you know, whatever, okay? for everything, okay?
For all the
For all the alternative hypotheses, okay? So that's it for the alternative hypotheses, okay? So here the data, you will have an x and an n, okay? Or, and from that you calculate p hat, which is equal to x over n, or you have n and p hat is given to you. Okay? They might not give you an x. Okay? Here you'll have x1, n1, x2, n2, and you have p1 hat, which is x1 over n1, p2 hat, which is x2 over n2, and then you have p hat overall, which is x1 plus x2 over n1 plus n2. This was from your homework last week, right? And the first problem that I did today, that I said you need to know for the quiz next week. Okay. One sample numeric variable, your data, you will have an n, an x bar, and an s. Two samples, numeric variable, you'll have an n, an x bar, and an s for each sample. And we just put little subscripts to indicate that it comes from sample 1 or sample 2. So again, when you read a problem, go through, label all the bits of information, and then your life will be much, much easier. Okay. The standard error. Square root of p hat times 1 minus p hat over n. P hat times 1 minus p hat over times 1 over n1 plus 1 over n2, square root of this entire thing. Standard error here, s over the square root of n. And standard error here, s1 squared over n1, s2 squared over n2. I'll post all of this stuff online. How's that? It's on the computer, right? And I'm saving it all. It's easy, all right? You should still take notes and pay attention, though. All right. So all of these, again, every one of these hypothesis test things, we got this, okay? So I'm going to just keep going on, and let me clear this out. Is that okay?
Hold on a second.
I'll give you 3 seconds.
Okay, you know it. Just go ahead.
Just go ahead. Sorry. Okay, so once you have your standard errors, then you calculate your test statistic. So here your test statistic is going to be z is equal to p hat minus the p that shows up in your null hypothesis divided by the standard error. Here your z is p hat 1 minus p hat 2 over your standard error. Here your test statistic is t is x bar minus It'll all be okay. Let me save this as 18 here. I'll post these online.
Where I can't find it.
I don't know what's going on, all right? They're there, all right?
I was just joking, man.
Here, we'll go there right now. We'll go there right now. You guys have this down? No? I'm 99% sure we got this here. All right, so this is the class website, right? See this? It says lecture videos right there. And I'll zoom in. Okay? I have about the final, about the midterm, lecture videos. All right? And then, all right, and then you just click the link. 19% right significantly different from 21%. Holy cow. Look at that. Okay. So I'll put these notes up there. All right, so here you then look up in the Z table. Actually, this applies to both. Oops. And so does this stuff here. So over here, you look up Z in the Z table. Okay? If has greater than, get the area to the right. If the alternative has less than, get the area to the left. Good. And if alternative has not equal sign, take the tail area and multiply by 2, okay? Always, sometimes a common mistake is they didn't take the tail area and you multiply by 2. Your resulting number must be less than 1, okay? For all of them, okay? Your resulting number must be less than 1. Okay? Because it's a p-value. A p-value is a probability. Probabilities always have to be less than 1. So if you're getting something greater than 1, you know you made a mistake. And over here, look up in the t-table with degrees of freedom equal to n minus 1, and use the small n if there's more than one n. Use the smaller n if there's more than one n. Okay? And for all of these, the conclusions is the p-value is greater than alpha, do not reject the null. We do not have evidence to support the alternative, okay? And if the p-value is less than alpha, reject the null and say we do have evidence to support the alternative.
How big of a sheet do you have? Just the same thing?
You get a 3x5 note card. Front and back. 3x5 note card. Front and back.
By 3 by 5, you 3 feet by 5 feet, right?
If you can find a 3 foot by 5 foot note card, I'll be impressed. But you cannot use a 3 foot by 5 foot note card either. Okay, 3 inches by 5 inches, standard stuff.
It seems a little small for all of this. I mean, really. And you didn't have our quizzes ready today? Come on, like a little breathing room here.
I'm gonna stand by my guns here. All right. But I appreciate your
You've given us like 20 pages of this.
I give you 18. This is the 18th slide here. All right. I can count here. Yeah.
Are you gonna email us our grade or?
I already did.
No, the quiz grade.
Oh yeah. So okay. So after next week's quiz, so you're gonna take quiz 4, and then I'll grade quiz 4, and then I'll email everybody's grade after quiz 4 because that's pretty much everything other than the final. And I'll say this is what you need to get. Whoa. This is what you need to get on the final. If, I don't. Okay. That's a fire alarm.